A very warm welcome to you all, to everyone who's attending, whether you're a member or a supporter of CED. We're very much looking forward to hearing what Malcolm is going to say to us. I'm just looking. Oh, you are still there. You've moved around on the screen, so we're very much looking forward to what Malcolm's going to say. He's been a member of CED for about 2 years. The video is going to be available from our website or on our YouTube site afterwards. You're very welcome. I'll just basically hand over to Malcolm now, who's going to talk to us about. Well, I'll let him explain.
It's how to find a well location. Let's put up the presentation. And can you all see that?
Yes. Do you want to put it on? You will put it on slideshow.
Yes, unfortunately, the meeting bar is sitting over my presentation bar, so not quite sure how to get rid of this at the moment. Just press, okay, that's good. I'm sorted down there. Right, we're good to go. So apologies for that, everybody. Good evening. My name's Malcolm Anderson, and some of you won't know me. So just to give you a bit of background, I'm a hydrogeologist. I've been working in the hydrogeology arena for about 35 years, and on everything from water supply to groundwater remediation. We'll see some of the examples of that in the presentation today. And in particular, the areas where my work has been concentrated are in the UK, inevitably, but also in the Middle East and Africa, and over the last 10 years, mostly in East Africa. And the talk today will mostly focus on the East African region. The talk itself is about well site selection and how to locate a suitable site for a well or borehole. But a lot of the principles also apply to springs. We will also just have a look at some of the wider aspects around the site selection, because we don't want to get into a situation where we're just thinking about one solution. We need to understand whether that's the best solution, and therefore you need to understand its context with alternative solutions like river intakes and so on. So we'll look at that range of source and solution. Now, originally, when I was asked to do this talk, the intention was that I was going to describe how to undertake a geophysical survey to identify the optimum location for a well or borehole. In reality, that's kind of a misunderstanding or misnomer. The geophysics sometimes works and doesn't. In some situations, it's fantastic, and in other situations, it doesn't tell you very much at all. So the best methods to locate wells are hydrogeological, and the reason for that is that in most locations you can find water. It's just knowing which layer to go for to get the water supply you want, and to make sure that the water quality is also covered as well. So with no further ado, let's go into the presentation and see how that works out. As Mike has said, it's going to be in two sections. The first one contains some background, so guiding principles, and it's a discussion on water supply options, and in particular an overview of groundwater recurrence, because it's very helpful to know what kind of groundwater environment you're in. Some environments, if you aren't a hydrogeologist, you will need assistance, and so it helps if you can recognize that. You'll know when to ask for help. But in a simple groundwater circumstances, then pretty much anybody can go through the process and come up with the right answer. And then the second half, section 2, is how you go through the process of a desk study to identify the best locations for wells, and that then ties into the second talk, which will be in about a couple of months' time, on the surveys, and specifically, or most importantly, geophysics, which for most people is a bit of a black box that is not is difficult to understand. Talk focus itself, as I mentioned already, will be on East Africa, and the relevance is to small scale water supplies. So that's, say, schools, hospitals, villages, hamlets and homes. It's not suitable for anybody on the internet who's looking to develop a water supply for a business. And if that is what you want to do, then please call me on the number you can see at the bottom of this page. I'll be happy to help you through my company, Fluid Solutions. So, as I said, this talk is the first of a group of 3. This one which describes what you need to do at the desk study stage to identify the optimum location for boreholes and wells. Talk 2 is the well and borehole design and surveys stage, and talk 3 is how you go about designing and constructing a well. Now, the reason there are these 3, well, yes, if I just back up to this. So the desk study process basically includes data collection, identifying what the water demand is. That's critical because the demand defines what's an appropriate solution. Identifying the water source options that are feasible, identifying limitations, constraints, and strengths of each solution, and then going on to identify the preferred water supply solution. Now, most of those things can be done at the desk study level. Similarly, we can, at the desk study level, we can do the basic hydrogeological analysis and identify suitable wells, sites within the site, where we want to go and where we don't want to go. And we can then make a preliminary assessment of whether we're going to need geophysics and leveling surveys and what have you. And because everything has a cost attached, and the best solution is always nearly always, not always, nearly always the lowest cost solution, then obviously we need to be cognizant of the cost of each of the different proposed options. Now, here's some guiding principles that are really helpful in this study process. Some of these will be familiar to you because they're standard engineering principles. And the first one is the value of doing a proper desk study before you start, rather than just saying, oh, well, it's so much more fun to go to site. Let's go to site. Let's travel to Tanzania or wherever it is, and let's go and look at the site. Yes, that's useful, but the opportunity to save costs reduces as the engineering value chain advances. So what do I mean by that? This is quite well known, but basically, if you have a typical site, over the years, you'll have the initial desk study, the surveys will be done, the design, the construction and operation, and then when the solution is operating, at some point it will need maintenance, and at some point it will need replacement. Now, what the water engineers have worked out over the years is that the opportunity to save costs is right up at the front of this whole process. It's at the desk study stage and at the survey stage when you're trying to choose a solution. So that's where you need to really focus and put in appropriate amount of effort, because in the long term you're going to save quite a lot of cost. And that applies at the village water supply as much level as it does at the large municipal scale water supply. And again, this will be familiar to all engineers. The triumvirate of water resources assessment pretty much applies in all water supply programs. So quantity. So here we're trying to focus on the demand, the capacity of each source, the storage requirements to match the demand against the source capacities during the day and over the months. And then looking at the resilience components, which includes the dry season, drought limitations, and the contingency plans you need to supply that quantity in those circumstances. And then quality is very important in groundwater well selection, because quantity is something that is typically a function of the the rock type that you're encountering, which will be true across most of your site in most cases. Quality, however, is very location specific. So you need to know where the hazards are, the water quality hazards are. You need to know the direction of flow, and from that you can then work out where you can put wells in and where you can't. So if quality is really important. You're asking questions of, are harmful constituents present? And those can be biological, chemical, or physical. That last one, by the way, includes naturally occurring radioactive minerals. They're pretty rare. In most circumstances, if you've got a dug well, you're not going to encounter norm. But if you have a deep well, there's a much higher chance. And so just be aware that that's an issue that you need to think about, but most of the time will not be an issue. And then obviously from a solution point of view, the best solution is to avoid water quality issues and have a well that is drinking water standard. And the main reason for this is that whilst most things can be treated, it's expensive. And at the village water supply scale, that's normally a showstopper. So, however, there are some solutions like sunlight and settlement and filtration that can just about be included. But keep in mind that those costs are not just the capital cost, but they're also the operation cost as well. Both of which are more expensive than a source that doesn't require much treatment. And then the cost elements, most of you will be familiar with, will come into most of those items during the discussion this evening. But obviously it depends on the water supply method, which will have different capital costs and operational costs. And then in regard to wells and boreholes, the access is critical because you need to get a big drilling rig in. And then you'll also need to think about power requirements for if you're planning on using an electrical pump. And then operation, treatment, and maintenance. Most of the time, you would be expecting limited treatment, and you're expecting a significant asset lifetime. Certainly, that's what we'll be planning and designing for. So this section here is the overview of groundwater assessment, beautifully modelled by Ian Rankin, looking at a dug well which encountered salt water, and we were discussing what's the next step. So here's an overview of groundwater conditions that will help give you some idea of identifying whether you have any risks in this water supply solution that you're proposing. And the first step of this obviously is to recognize the groundwater environment you're in. Now, it will seem obvious once you've gone through this, but forewarned, forearmed. Remember that hot does not equal dry. So if you have, in most of the tropics, most of East Africa, there's a plentiful of rainfall. So that would be hot and wet, not hot and dry. But some locations are absolutely desert, and I'll be showing you some pictures of those. And obviously those are hot and dry, not hot and wet. So in most cases, just because farming works better in wet environments, the water supply solutions that we're looking at will be in wet environments. And so that applies here in Britain as much as it does in East Africa. You tend to find people living where they can farm, not in the desert where it's much more challenging. That doesn't mean to say that there aren't people living in the desert who need water supplies. Now, the key thing about wet environments is that the groundwater overflows and has will typically have a short flow pathway from locations of hills to the nearest river or spring discharge. In other words, it's essentially a shallow flow system, and those springs sustain the river flows, and you get continuous perennial rivers that flow through lakes and down to the coastlines. In dry environments, it's not like that at all. What happens is the rivers will be suspended above the groundwater level, and so the rivers will be losing rivers, providing water through infiltration of the riverbed into the groundwater system. And that groundwater flow is then what reaches the low point in the groundwater system, and that will either be the ocean margin, or it will be salt lakes, of which there are many examples in the rifts of East Africa. So here's some pictures of some wet environments. This one's from Ethiopia, and here you can see villagers have walked up to the spring, and they're collecting the water and taking it back home. This, of course, is very different to this picture, which is also from Ethiopia, which is from the Danakil Desert. And let's see if my pointer works. Can you see the pointer, everybody? You just wave a hand if you can. Yep, great. So this example here on the right is a dum palm. You can see it sitting in a channel, which is a ephemeral runoff channel that runs off whenever there is flood runoff from rainfall. And this tree is really helpful because it has very shallow root system. So we know that it's drawing water from this ephemeral flow system. So we know that just by seeing that tree that the flood runoff occurs through this channel here. And then on the left here, this is the classic acacia tree. Acacia trees have root systems that can go up to 20 meters deep. It's complete opposite. It's actually in virtually the same location as this palm tree. The palm tree is it's down in the horizon, and here the groundwater level is quite a lot deeper. But this acacia is surviving because it's able to capture moisture from 20 meters down, and so it has a completely different system of survival. So that just those two different trees tell me how deep the groundwater system is. I know that in this location on the right, groundwater level is likely to be close to ground surface. And just because this tree here and the environment here is such that they only get 2 or 3 good rainfall events a year and runoff events. So it would be difficult for that tree to survive unless the groundwater was close to ground surface and isn't too salty. Whereas with the acacia tree, it doesn't tell me too much, but it probably tells me that the groundwater level is quite a lot deeper. So that's a desert environment. If you get into a desert environment, then that's one of the environments to give me a call. If you're in the previous wet environment, then most of the conclusions that I will give you today will just follow through just logically. Salt flats. So these are areas that people generally don't understand. So those of you who've seen the speed records in America on Bonneville, that's a salt flat. It's just like this one here in Ethiopia in the Danakil. And here you can see a sinkhole with the groundwater level in the sinkhole. This is groundwater. It shows you that the groundwater is only 30 centimeters or so below the ground surface. And what's going on here, and the reason why this is a relatively dark brown is because the groundwater is rising through the soil here through capillary rise and is evaporating from the surface of the playa. And then every time it rains, all the salt that's on the top here that's evaporated and been left behind then gets dissolved and washed into the center of this particular part of the rift. And there you have halite deposits of salt, the salt rock essentially. And so that's fairly typical of a salt flat in East Africa. And as you can see, here's the rift margin along the side with the mountains on the side. Incidentally, so there are other shots here. Here's some more, a whole load more sinkholes. These are associated with faults that are inside the salt, and you can, when you track these sinkholes, you can track where the fault is below, and the fault is what is releasing the fresher water into the salt zones behind underneath it, and that's causing the dissolution that's causing these sinkholes. Right, so this here, another form of flow that you get in groundwater systems in East Africa is gas lift. There's a lot of volcanic activity which releases CO2, H2S, and methane. And the main one is CO2, especially in the East African system. And this is what a spring that's being caused by CO2 release looks like. So I won't really dwell on that, but clearly that's not a normal groundwater flow. That's the gas lifting the water into those stalagmites and creating stalagmites. Incidentally, they're not calcium carbonate. That's halite, and this is all halite rock here in this particular location. It's very similar. It's very close to the previous shots I showed you. Oh, just jump past that. The volcano environment, same thing again, but here the previous version was just gas, so it was cold. This, what I'm going to show you now, is Mount Dalol in the Danakil, which is a solfatara volcano. It's about 40 meters above the rest of the playa. And the reason it's 40 meters higher is because the hot water that's underneath it is a lot less dense, and that just lifts the water up into the volcano. And we'll just show you some shots of this. This is what it looks like on the volcano. And then hopefully I can now play again, here you can see the water coming out of, this time, a stalagmite. It's also salt, but the steam tells you that it's a different story, because the water's coming out around about 120 degrees. It's superheated, and as it rises, the steam forms, and then that creates gas lift, and that then comes out the little spout here. This is just one example of lots of little different vents you see all across the Solfatara. And the reason why everything is yellow is because it also contains sulfur, which then sublimes and leaves the yellow staining everywhere. There's also iron in there, which also adds to that. So in those group of three pictures, we have the wet system, which was the first one where the family were collecting water from the spring. And then I've shown you a number of other different environments which are more extreme, where specialist groundwater knowledge will be helpful, and that's a good time to call me. So this slide essentially is covering that and saying what I just described, and saying that if you have a more complex environment, then just call. But if you've got a fairly straightforward system, then have a crack at it. It's not that difficult. Okay, so just an overview of groundwater flow. This again will be familiar to those of you engineers. I'm going to keep it as basic as possible, but I don't think there's any need to complicate it. It's, as I say, the main purpose here is identify whether it's something that's simple, in which case have at it. But if it's more complicated, then give me a call. So the main comment here is that pretty much all rocks transmit groundwater, but only the most permeable dominate. And groundwater flows from high to low level, taking the shortest route. It's actually flowing from high to low potential if you're an engineer. The groundwater level is set by the outflow level, and this is something that really helps in terms of trying to get to grips with how the groundwater is. If the groundwater is flowing into a lake, then that lake level will be the lowest point in the groundwater system, and all the groundwater level from there will be higher because it has to flow downhill to reach that lake. Similarly with the ocean, groundwater levels will be above the ocean level as you move inland. And similarly, if you have an internal drainage system, which is what causes all the salt from the lakes, from the evaporation, the fact it's salt tells you it's an internal drainage basin, and that is the end of the system. And that level will then tell you that the groundwater levels around the lake will be higher. So rock type is critical as well. And so the key ones that we're really interested in from a borehole point of view are sands and gravels, sandstones and limestones, because they support high yields. If you have those in your where you want to supply, you're pretty much done and dusted, because they will reliably produce water supplies with very few borehole failures. Siltstones and fracture rocks support moderate yields, and in the case of silts and silts in particular, so this is alluvium, you'll get a reasonable supply, certainly sufficient for most of the small scale supplies that we get involved in. But if you're in siltstones or fractured rocks, the fracturing governs the local permeability. So either the well is connected to a fracture system or it's not. So with fractured rock, then the chance of getting a dry well increases. And that's mostly a matter of chance because there's very little way of avoiding that. But knowing that risk in advance helps because you can build that into your understanding of what the cost and risk of the solution is. So there's a further comment on the unfractured rocks. The other rock type we avoid are clays because they are pretty impermeable. They're not impermeable, they're just much lower permeability and unsuitable even for low yield wells. However, clays themselves also often contain layers within them that are good producers. So an example would be the Weald clay in southern England, which has the Tunbridge Wells sandstone in it, which is locally a very important water supply. But if you look on the map, it just says Weald clay. Certainly if it's a regional map. The other key thing to keep in mind in Africa is the weather profile, sometimes referred to as the saprolite. It's a variable depth because it depends on how far where the water table is mostly, and the extent to which rainwater percolates down. The process of percolating down brings down oxygen and acids into the saprolite and causes weathering over a long period of time. Now that's a real boon for water supply because the top 10 to 40 meters will typically be soil rather than rock. And because it's porous rather than fractured, you'll typically get a reasonable supply in that top 10 to 40 meters. And then in the zone from 40 to 80 meters, you'll get some solution enhancement of the rock fractures. So that means that a well that is 80 meters deep has a pretty good chance of getting a supply. But your optimum supply zone will probably be 10 to 40. This is a generic model. It won't apply everywhere, but it's a reasonably good thing to keep in mind. And then from 40 to 80 meters will be a reasonable supply, but it won't necessarily be a large supply. And of course, the exception to the rule is if you hit a good fracture, it'll be a very good zone in that bottom 40 meters. There is a fair amount of variability. It does require a change in mindset from being an engineer to be a hydrogeologist or a geologist in general. Hydrogeologists measure in meters and think that's grand. Engineers measure in millimeters and get upset if anything's out. So it's a completely different mindset. So you're probably making statements like, well, it may or it may not be will be probably disappointing, but we're basically happy with taking a certain level of risk. And what we're doing every single time is making a risk assessment as to what is the least risk solution with the lowest cost. And then if you get a dry well, that's not a fail, by the way, that's just a dry well. That happens to everybody. And if you get a low yield well, that's not a fail, that's just how it works, just how it goes. There's a certain amount of chance involved. What we do is maximize our opportunity of success. That's what we're trying to do. Sorry, folks, I'm struggling with the picture bar here because it gets in the way of my titles and other things. So the good news is that for the kind of water supplies we're interested in, we don't need very much. So in most cases, we won't have an issue. It's only when you're at the municipal scale that it's really important to get good yielding wells. But then they've got bigger budgets, and so they can cope with that. So it all works out in the end. Okay, so here's a question for you. Where is the water? So this is again a shot of the Danakil Desert in Ethiopia. And quick glance at this photograph tells you that there's limited rainfall because there's no vegetation. It's obviously a dry area. And because it's a dry area, we know that the river here is ephemeral. And because of the slopes that we can see, we should be very concerned about flash floods. The nature here is that basically you'll get a flash flood and that'll be enough to move boulders the size of a double-decker bus. It'll certainly sweep away anything in its path. And then you'll then get a tail to that runoff for about a week, in which the groundwater in the sands and gravels in the bottom here drains down. But then that'll be it for the next 3 to 4 months. So the Wadi runoff isn't really a solution because you've got to build a big dam, and that's far too expensive. And what can you see here? So there's actually 3 or 4 different rock types you can see in this photograph. So this line here demarcates between the limestone, Jurassic limestone in front here, which is the what the French would call café au crème, so coffee and cream color, and that's the Jurassic limestone. And then behind you've got Neogene Bannakill siltstones. These are red beds, but silty rock. And in both those cases, you get a high to moderate flow rate in the limestone, and you get a low to moderate flow rate in the red Danakil sandstones. If you saw both of these in our, and we wanted to put a supply for a school, both would be fine. They both have good enough capacities. And then there's another boundary that occurs where the new green line, dotted line is. And then behind that, and this will be a little bit more difficult to see if you've got a small screen, but you can see in fact, I might even put the next boundary. If you see that green line, that between the light green and the darker green is an alluvial fan. And it is what it says it is. It's basically fan shaped, and all the sands and gravels that come down this wadi debouch at this point at the top of the fan. There's quite a strong slope on this fan, and then that water then runs off across this zone like a delta does, moving backwards and forwards, and deposits those sands and gravels, and you end up with a fan-shaped sand and gravel deposit. And that has high transmissivity, so it's a very good place to look for water. And then at the far end, this is the salt playa we looked at earlier along the horizon. So ignoring the fact that the water quality aspects, the salt rock playa is karstic because of the dissolution of the salt. So you get a moderate flow rates in that karstic salt. So as it turns out, groundwater will work in pretty much all these locations if we were not sensitive to water quality. So also show something on the faults, because that last picture had a number of faults in it. So the reason why faults are important, and by the way, the reason I'm showing these from the desert environment is because the geology is exposed really well and you can see it, and that allows me to explain what's going on. You'll have those, the faulting and everything else, and the different rock types will also be present in any rift margin in East Africa. And I'll explain how you work out what to do when you're in an environment where everything's covered by vegetation. So faults. Faults are really important because they impede flow and act like dams and weirs to the groundwater flow in the aquifer due to the low permeability caused by the grinding of the rock in the fault itself. That produces a fine powder called fault gouge. And the other reason is intrusions in the fault plane. However, ancient faults and intrusions are well fractured, so provide moderate permeability because the whole fault system becomes lithified and then gets flexed and broken over time. And then so Precambrian, so dikes in the Precambrian or other intrusions in the Precambrian are actually targeted by South African hydrogeologists to provide water because they have enhanced fracturing compared to the Precambrian rocks outside the intrusions. And that's because you've got a narrow rock with a different rock type, and as you flex it, that's the bit that cracks. So it's not always the case that faults are impermeable. Now, the other thing you need to take into account is that the faults locally have high transmissivity parallel to the fault on either side. So if a flow is trying to get across that fault, the transmissivity and permeability is low because of the intrusions and the fault gouge. But parallel to the fault, the opposite is true because the flexing that occurs on either side of that fault to accommodate that movement creates a whole load of fractures that then create high transmissivity. So essentially that fault acts like a barrier boundary, and then you get enhanced flow in parallel to the fault. So if I go back to this previous picture, where's the structure? So as I said, the Jurassic limestone is in the foreground, red Denical siltstones in the middle of the picture. And the Danakil is quite a lot younger than the Jurassic, yet it's at the same level, if not lower, which tells us that the red dotted line is a boundary fault, which in the context is a rift boundary fault, and the throw on that is at least 200 meters. We can do the same at the far end of the Danakil, much the same throw, about 200 meters or so. And that's because rift boundary faults are very rarely one, which is how they're typically shown on a map because of the scale of the map. It's actually a whole series of them lined up, running down into the rift. This is something that frequently occurs all across East Africa because rifting is such a common feature within the hydrogeology of the region. Sometimes these faults are small, with small throws, sometimes they're large. Again, if you can see a classic rift with a valley floor long below you, there's bound to be a rift fault nearby you. And then because of the anisotropy of the flow, what goes on here is that the flow in the Jurassic limestone goes from right to left as it heads towards the rift. So it turns out that this alluvial fan here is quite a poor water supply solution, and the one next door is very good. And it's entirely due to this fault and the orientation and the information I've just given you. Another shot of this same fault. So the last picture was taken from the top of this mountain here in 45-degree plus heat. It's very hot here. And then there's the slope and the plane of the fault. And this here is the red Danakil formation. This is the Jurassic limestone. And in the middle here is the intrusions that have come into the fault as it's moved. And there's another shot of that here a bit closer. So there's the zone of the fault. Here's the intrusions. Here's the Danakil formation. And there's the intrusion, and there's the Danakil on the far side. So what about water quality? I think I'm going to have to move on a bit here, but I think we're doing okay for time. So here the water quality is fresh here in the limestone because you've got the hinterland behind you with the rainfall and the runoff that's filling up the limestone, and then as I said already, because of the faulting, it heads off from right to left. The salt playa in the far distance, of course, is salt, so that's brine. The Danakil itself here is brackish water, but the only water that comes into here is once it crosses the fault here, it then gets water coming in. But the other thing that's going on regionally is that you've got groundwater flow from behind me coming into this rift. And so you've got deep flow that is then forced up into this zone because the salt water and brine is more dense than the fresh water and the brackish water that's at depth. So in this zone, you're getting upwelling of groundwater, and you tend to get brackish water. And in the fan at the back here, you get, if you pump small amounts of water close to the Wadi runoff, you'll get fresh water because that's what infiltrates from the Wadi runoff. But if you pump it hard, you end up with increasingly high salinity and very bad scaling problems. So from a water quality point of view, the best solution is this Jurassic limestone or the next wadi along. It's a fan on the wadi next along. So understanding your system is quite helpful. It does vary quite a lot. A desk study will sort out all of those components, providing you put time into it. So this is section 2 now, which is the well and borehole site selection process. Does anybody know how to get rid of the people at the side? Am I able to get rid of that? Because I'm having to hunt it around my screen all the time to see things.
Top right.
You can change the view.
Oh yeah, okay, I got it. Hopefully we'll sort that problem out. Thank you, folks. So the desk study steps. So obviously the first step is to determine the water demand from the solution you want. Data collection, as in all projects at desk study stage. And we're looking specifically for geology, topography maps, anything on hydrology and hydrogeology. Data analysis, as always. Identify feasible water source options. We'll go through that in a moment. Identify limitations, constraints, and strengths of each source option. Identify preferred water supply solution, and identify suitable well and borehole sites with or without a cistern option, because they're complementary. And survey requirements and the cost. We mentioned this previously. So this slide here is just an example for a data search that you've got to carry out. Of interest is this picture here, which I don't know whether you can read it on your screen, but it says here Musley 1964 weather home on this base plate here. And this is a larger picture of this. This is a famous place in the world of hydrology. It is the place where the hottest annual average temperature has ever been recorded. And that was in 1967, I think it was. But this is ground zero in terms of temperatures measured on Earth. And it still exists, well, just about. So it's a useful little place to have a picture of. So in collecting data, it's very helpful to have rainfall and evaporation data, ideally monthly, ideally daily, but monthly is okay. And in particular, at least 10 years. The monthly average data is okay. And here's a couple of websites that can be searched. The climatedata.org provides 10-year data for most locations. But equally, there's the National Meteorological Office and the Water Resources Offices, but they will typically charge you for data. A geology map, those can typically be found on the internet for free, and they'll typically be colonial era. They won't be as good as the latest ones, but they usually will be good enough for our purposes. Topographical maps are very helpful. These can be purchased through appropriate organizations. I typically use Eastviews Geospatial. Those maps give you a lot of information, as we'll see shortly. Hydrogeological reports. The British Geological Survey and Groundwater Unit has published a lot of reports on most countries throughout Africa. So that's always a good read to find out what is the likely yield from each of the different rock types that you get. Having somebody who's on site is really helpful, because a water use survey of neighbours in the surrounding area to find out what their water solutions are. Do they use wells? Does that mean that the boreholes are not viable? Or do they use boreholes, in which case does that mean that will apply to my area too? And an internet search for any geological papers and other relevant information is always helpful. From a textbook point of view, the textbook I always use is Raghunath, and it's an old version, the second edition from around about 1990. It's printed in India and has it's actually in very fine paper. It's almost like reading a Bible, but whilst it focuses on Indian hydrogeology, it's very transferable to Africa. So that's a very good text. There is now a third edition that came out in 2007. I don't have a copy. So if it contains more advanced methods, they may not be suitable. So it may be the second edition is still the best one, but that's a good text in general. Okay, the next section is to identify available water sources. Here's some springs in Ethiopia. I've got a list of 8 here, including the most likely suspects: cisterns, springs, rivers, dug wells, boreholes, and excavated pits, and methods that I call Muhammad's Mountain. I'll explain what that means when we get to it. So here is one of the cisterns that Ian Rankin has pioneered. As you can see, it's got rainfall running off the roof of the schoolhouse that then runs into this cistern, which is a 2-meter cubed system, and that provides drinking water for the Amani Hope Story School here. And then Ian is standing on a well. We'll come to that in a moment. Small springs, which can be just stuck at the side of a river or pretty much anywhere. This one's in Ethiopia. It's got an overflow and then a couple of pipes sticking out the bottom, carrying the flow to the villages below. It can also be, springs can also be large. This is an example from England. And incidentally, this spring also has a weir in it, as it comes out of the spring into these culverts. Comes out the culverts here when it's wet and then goes over this weir, which is what you can see here in the wet condition. Dug wells and boreholes. And boreholes come at lots of different scales. So this here is a 4-inch well, I think it is, which will take a 2-inch pump. So it's a really small scale and suitable for village supply, but with a small yield. This well here is the complete opposite to that. This is a rig drilling a 2-kilometer deep borehole that has a capacity of 6 megaliters per day. So completely different. Whereas the one on the right here has a capacity that's likely to be in the range of around about 2 liters per second, something like that. Now, water supplies can be quite basic. They can be a pit in the ground, but obviously there are water quality issues around that. And water supplies historically use different forms of tankers. So here's a modern version of a tanker, where they're sucking up the water from a lake. It's actually a discharge from one of our pumping tests. And then the traditional method of tanker with this donkey, which is a great picture. I really like this picture of the donkey. But that's how it's done in Ethiopia. They'll walk to the spring, fill up their water tanks, and then bring it back. And you've seen the picture here of the spring and the folks picking this up. This is one of the donkeys that's used in that process. But this is what I mean by Muhammad's Mountain. Muhammad's Mountain is, if the expression is, if the mountain won't come to Muhammad, Muhammad must go to the mountain. So here you can see the villagers going to the river or spring to do their work. These girls are doing the washing, because most of the washing water, most of the demand is washing water. So it's much easier to take the washing to the river or spring than bring the water back home and do the washing at home. So that's how it's done traditionally, and that completely changes when you have a pipe supply, because then they can do that all at home and it saves an awful lot of effort. Now, this next section, most of you will be familiar with: identification of water demand and optimal supply solutions. So I won't spend too much time on it, but it's always good to have a context of, is my groundwater solution the best option. I don't want to have myopia and just be fixed on my solution. I need to understand its context and whether somebody else can produce a better solution. So that's what this section's about. So typically in rural Africa, the demand per person per day is 20 to 25 litres, of which 15 to 20 is the washing demand, as we just mentioned. And that leaves 4 to 5 litres as the drinking and food preparation demand. And note, demand increases substantially with lifestyle and affluence. For instance, the UK water demand during my lifetime has increased from 70 to 150 litres per person per day. Irrigation will be on top of that 20 to 25 litres, and that's calculated from the crop demand. And that's explained in Raghunath. I'm not going to go into that here. But obviously there's a peak demand during dry seasons if you're growing crops during the dry season. And in business cases, they'll typically have meters, so you can calculate that from the meters. So again, the triumvirate of water supply assessment, remember it's quantity, quality, and cost that we're using to assess which is best. And here, the quality is one of the big constraints because it's one of the biggest costs, and it's often the one that gets left off. People, it's easy to fall into the trap thinking it's just the water supply quantity that I want, but the quality often is where the cost is. So in the case of river, lake, and dug pit sources, there's an inherent particle and biological hazard, and sometimes a chemical water quality hazard as well. And those water quality exceedances will require treating. So they will require, as a minimum, sun and UV irradiation and settlement or filtration. Another component of cost that's important is pipelines, which Barbara will tell you, is that the further away the solution, the greater the pipeline cost, and that often is a significant number. So again, if you have a river or lake solution that's some distance away, which they typically are, then that's an important cost. But if you've got the lake solution that's right next door, then that quite often is the best solution. The halfway house between boreholes and surface water is springs, because they, if they're covered, they don't typically require treatment. And so the proximity of the spring and pipeline to the supply demand is the key. But one thing to keep in mind for all of the well, borehole, and spring solutions is that they can be contaminated by upstream groundwater flow reaching the spring or borehole. And so contaminant locations like petrol stations are very important to be included in the DEST study. Dug wells and boreholes typically don't require treatment because normally the water is of drinking water standard. However, there's a caveat to that, because especially with dug wells, you've got somebody inside the well digging it when they're digging it out, so it will be contaminated by dermal contact, and it will need disinfecting before it's put into supply. Similarly with boreholes. In terms of cost, dug wells cost about £5,000 per well and have a limited capacity of, say, 1 to 3 meters cubed per day. Obviously, that varies over time, and that number could be as much as £6,000 or £7,000 by the time we get to use this. Boreholes vary in cost depending on diameter, depth, and can vary between 5,000 and 30,000. And it depends again on jurisdiction. And the capacities are obviously significantly greater, so you're getting more water. It's actually a cheaper solution, providing you have the demand for it. So if your demand is 10 meters cubed, then often the borehole is the best solution. Obviously, the main advantage of dug wells and boreholes is that it can be sited right next to the demand, which limits the pipeline costs and makes them easier to manage and more secure. However, as I mentioned with the springs, you have to be very careful about siting them, and this is the main crux of this presentation. you need to make sure that latrines, petrol stations, and graveyards and so on are not close nearby. And this table basically summarizes the various solutions and what they're likely to yield. I'm not going to labor on this because this can be downloaded if you want to from the site after the talk. But essentially, the system one is the odd one out here because you can fill a cistern every time it rains, but if you during the dry season, it won't rain at all. And so the capacity of the cistern is key here compared to the demand. Now, let's say the demand is a family of 5 with, say, 100 litres demand per day, and you've got 2 meters cubed in your tank, then you've got 20 days of supply. And then during the dry season of 3 to 6 months, that's not going to be good enough. But it is a fantastic backup supply if your mains water supply or your borehole goes down. So cisterns are really good backup supplies. And unless you're in an environment where it's regularly wet, in which case it can also be a primary supply as well. Rivers, impoundments, and sand dams, you need to watch the water quality, but they can often provide high capacity solutions. Similarly with capped springs. Dug wells, limited supply. You have to be careful with the water quality because they need to be properly capped, just like capped springs. And then boreholes at different sizes can produce a large difference in capacity depending on what kind of rock formation you're in and what's suitable. But in our case, most of the time, a small capacity well is going to meet the demand that we need. So here's the groundwater quality assessment. This is probably the key area to take in. As I said, the biological hazards are mostly bacteria and amoeba, and these ones either get into the wells and boreholes by the people digging them out or working on the pipe work as they're drilling the borehole, or it can reach the well through the groundwater system, especially if you're in sands and gravels or fractured rock. And here are the 3 main pathways from a nearby pit latrine, and you mitigate that by being upstream or sidestream of the latrine, which requires you to know the direction of groundwater flow. And if you're downstream, you need to be at least a 50-day travel time, and ideally put a factor of safety of 2 on top of that. As I said, the well users, diggers and roughnecks will contaminate the boreholes when they're first constructed. So disinfection is important after construction. And the other thing to take into account is flood ingress into the top of the well or borehole, and that's mitigated by having an appropriate concrete sanitary seal to prevent that water ingress. And then on the chemistry, this often can't be easily rectified, so care in the well site solution is important. Don't put it downstream of a petrol station. Avoid road verges because you quite often get a concentration of PAHs from the runoff off the road. And the reason, and also avoid factory discharges. Incidentally, just keep in mind that the contamination from petrol stations can often be as much as 2 kilometers downstream. So some rules to follow during site location. So in addition to making sure that the site is upstream or sidestream from a particular contaminant source, you also need to make sure that it's outside of the capture radius. And the capture radius can be most easily thought of. If I pump my well at 2 meters cubed per day, then over the year, I'm going to pump in the region of 700 meters cubed out of the ground. And if my ground is ground unit is aquifer unit is 2 meters thick, then I need a sufficiently large surface area to get that water out of. So that water will be needs to be some distance from the hazard. I'll show you how to calculate that in a moment. Obviously, you need an adequate sanitary seal, and those are two comments I've already made, so we'll just move on that one. Yeah, I think we've done all those. So how do we do the hydrogeological analysis? As you know, basic rules are groundwater flow is perpendicular to the contours of equal level, so it goes downhill, following the slope on the groundwater level contours. That flow system is amended by the geology, rock type, structure, and outcrop geometry and the sequence of layers. But generally, in most systems, they effectively behave as a homogeneous system. So you don't really need to worry about number 3 most of the time. So here's the example, and this is actually taken from the project we're currently working on in Tanzania. And the site location is here, close to the location which is marked as Impirani. And this is a colonial era map, but it shows us all the information I need. And in particular, it shows me that all the streams that are draining into this dam are all on the 120-meter contour. You can see that one there. Hopefully you can see this on your screen. That one there is on the 120-meter contour. This one is close to the 120-meter contour, as are this one, and this one. And that tells me that the groundwater level is around about 120 meters, and I can draw a groundwater contour where those spring lines emerge, because that's telling me where the groundwater level is. And that is what that line is. That's the 120-meter groundwater level contour, just drawn straight off the topographic map. And similarly, you'll notice that these two streams here start here and here at a higher level. That's 120 meters there and there, but they go some distance further. So they're around about 130. So I can put in a notional top to this system of 130. And the reason I know it's the top is because here I've got streams discharging from this 120 in that direction towards the north, also to the southeast, and also to the northeast. So that means this must be a local groundwater high. Now that I've established my 2 levels, I can incidentally, the reason this one is this length is I'm just trying to keep contour distances between the 2 of them about the same width, because the groundwater flow will be roughly the same and therefore require roughly the same slope, and therefore you should get roughly the same geometry of the high to the previous contour I've picked out. So from that I can then put in the groundwater flow directions to each of the streams. And then in my site itself, then one of the possibilities is that the flow is towards the northeast. But compared to the nearest discharge location, which is the spring here, to the site, that's the shortest route. So that's the one that I'm expecting the groundwater flow direction to be, just because water takes the shortest route. And now I've established the groundwater flow direction that I need to be most cognizant of on my site. And so I need to make sure that I don't have any water quality hazards on the, as far as possible, on the the west-northwest side of any particular well site location that I want to put it. Now you'll notice that that's a really quick process, and it's all desk study based, and it tells you a lot more in terms of the lot more than a geophysical solution will tell you. And as I say, the desk study is the point where you can save costs. So just this simple little exercise is worth its weight in gold. And we can use it to identify the approximate groundwater flow direction. It doesn't always work, but it's a good first estimate. So in this picture, see how many hazards you can identify. Because time's a bit pressed, I'll just go through these. So there are a couple of toilet block houses. There's one here, and there's one here, they're pit latrines, so they're definitely hazards. Another hazard is the people themselves, because the people have the hand to mouth is one of the directions in which water can get contaminated. But we're not an issue today because everybody's got their sodas today, so they're fine. And the other one that's not obvious, because it's basically a trick question. In these trees here, there is a graveyard, so we need to be wary of that graveyard and the downflow from that graveyard. The reason for that is historically, bodies were often buried with some fairly nasty chemicals, so you never really know what's downstream from a graveyard. I'm going to skip this one because we've gone through the water quality hazards and discussed this. And now we're just going to look at the capture radius calculation. So the equation I've just put up here is fairly straightforward. If you know how much water you're going to pump from the well, which is the Q, let's say it's 2 meters cubed per day. And let's assume there's one rainy season per year. So we'll assume that that's going to be pumped for 365 days of the year and then get replenished. So that's the T value. Because it's silts and sands, we can assume a fairly conservative porosity of about 10%, and which is the S value, storativity, and the thickness of the depth of the well is 2 meters, which is a good indication of the aquifer depth that's being sampled from. And from that, we can then calculate what the value of RCW is, the capture width radius. And that gives us an answer of 35 meters. So I want to make sure my well is more than 35 meters from any hazard. And in fact, you would then put a factor of safety of 2 on that and say, okay, 70 is really where I want to be. Similarly, I can do an infiltration radius to make sure it doesn't exceed or is less. And as it turns out, this one is, the capture radius is larger than the radius, infiltration radius, and that is the radius of, so if I take the rainfall and take away the evaporation and take away the runoff, which in this case is 0 or close to 0, and use reasonable values for the site, it turns out that the well will be replenished by rainfall within a radius of about 30 meters. So that's very similar to the capture radius. So if there's insignificant flow across the site, that rainfall will be replenishing that well within that 35 meter radius. So that means, again, if any hazard is at 70 meters, I'm reasonably in the clear. But ideally, I want to be side gradient or up gradient from the hazard. Now, in travel time or travel distances, you calculate the velocity, and that's calculated from the contour interval, which is from the previous map that I constructed. And I can use those values to calculate that the gradient is about 2%, meters in distance and meters in height is 2%. And then the K is unknown prior to the test, but the well was in silts, or is expected to be in silts, and so we can expect a value of 1 meter per day. And when we calculate that then gives us a velocity of 0.02 meters per day. And in groundwater, we don't worry about the porosity, but that's the distance over the ground. So that means that if I have 50 days, it'll travel just 1 meter. So in a silty condition, that's not an issue. But if I'm in fractured rock or sands and gravels or a sandy rock, then obviously that's going to be a factor of 100 at least higher, and then it becomes important. So this calculation is important. It tells you how far downstream you need to be. And if it's a petrol station, just don't go there at all. You just need to be side gradient or up gradient. I'm just going to move on from there. Sorry, the reason I'm rushing a little is because I'm a little beyond the time, so I just want to make sure I just close this out. And what this little chart shows is that when you're working with small demands, there's typically a very small area that's impacted. But the larger your demand and the higher the flow rate from your borehole, the larger the capture radius is, and therefore the further you need the hazards to be. So it's important to do that for each of the solution that you're planning and the flow rates that you're planning. So this is the final few steps. So we've covered water quantity, which is governed primarily by rock type. We've covered water quality, which is governed primarily by the proximity of hazards and their position relative to the proposed well site. And we need to make sure our well sites are up gradient or side gradient or a considerable distance downstream. But other considerations are still important for groundwater and well supplies, and access is obviously the key one. The rigs are heavy 6-wheelers and will sink into the ground, especially after they've been pumping quite a bit of water. So most drilling drivers will not want to move very far from the road. In this particular case, we had to negotiate to get them to here rather than stop right on top of the school car park because we didn't want it inside the school ground. So whenever you're siting somewhere, it's really important to consider the access and whether you can get a heavy drilling rig in. The great thing about dug wells is that everything can be carried in on a wheelbarrow, so you don't really have the same issue, or a motorbike. So dug wells can be pretty much put anywhere, but if you're drilling a borehole, access is key and very important. Obviously, power supply is important. If you're in the middle of nowhere, then you're not going to have any power. So your solution is generators, which are expensive. So if that's the case, then you probably want a gravity feed system. So maybe boreholes are not your solution in that environment. Maybe it's the only solution. So the next step is to identify the actual well and borehole sites, but it's just a question of going through each of those steps one by one for each site and making sure that you have the right location. And these are the components you have to look at. So the demand center, the drilling rig access, the water quality hazards, the groundwater flow direction and any other hydrogeology considerations, the travel times, and then at that point, you're then going to select which are the best sites and deselect any of them if there's a water quality risk or access risk identified, and then select the optimal sites from the remainder. Obviously, this last one is fairly obvious. If there's nothing feasible, you're going to have to use a different water supply method. It's one of the reasons for making sure you understand the context of the groundwater supply in the context of alternatives. So that's it, folks. Conclusions. Determine and define water demand. Determine the hydrogeology using desk study data of geology maps, topography maps, and any other hydrology data. Identify a preferred water supply solution, which in this case, we're assuming is going to be boreholes and wells, just for the sake of the presentation, but could be something else. We identify water quality hazards and safe distances, access and power constraints, and then identify the well and borehole site options. And as I mentioned in the review of the different solutions, that can often be with or without a cistern option to provide extra resilience. And then you determine where you want to carry out or surveys, which is the topic of the next talk. Now, I haven't talked very much about cost in this, partly because of the time available, but each of those water supply solutions has a cost tag attached to it, and one of those will be the cheapest and the most reliable, and with the best resilience. Groundwater solutions provide all of those, but the risk is in the construction in the first place, because until you've actually constructed, you don't know what water quality you're going to get, and you don't know what water capacity you're going to get. So there's a certain, in groundwater is a certain amount of a leap of faith, but if you do that, often you'll get the best solution. But if that leap of faith is something that you haven't got enough cash for, then another solution is probably the better way to go. So thank you for listening, and that concludes the talk.
Thank you so much, Malcolm. A huge amount of work has gone into that. So a huge thank you. We really appreciate that. Very thorough. And yeah, I'm sure there'll be questions. I've got a list of about 8, but I wonder, will people you either put questions in the chat and I'll ask them, or just put your hand up if you like, or just unmute yourself and fire away with questions. I'll remove the spotlight from you so that you're on mine. You're extra large, Malcolm, but I'll remove that. So ask away. Go ahead, Nigel. The floor is yours.
Thank you very much. Hi, Malcolm. Thanks so much for that. That was brilliant, actually. I was just interested in the relationship between the river source in a desert and a wet environment. For the wet environment, I think you were saying that basically the water table feeds the river and is controlled by an outlet level, whereas for a desert environment, the rivers tend to the actual water table tends to be below the river. The rivers are perched above that. Are there any, if that's correct, are there any sites where it alternates seasonally between the two?
Yeah, spot on, Nigel. That's a cracking question. For the sake of brevity, I just took the two extremes, but there is an in between, as you mentioned. So in the wet environment, the groundwater takes the short route because the system is essentially like a full tank, and when it rains, the flow then flows to the outflow point, which will be a spring or lake or riverbed, and sustains the flows in the river. And so the reason why you get perennial rivers is because the groundwater is constantly discharging into that river system. In the desert environment, as you say, the river is now perched and is above the groundwater level. So now the riverbed is releasing water into the groundwater system. So it's a linear infiltration system. And then in some environments where the groundwater level is fluctuating between above river level and lake level and below river during the rainy season, and then below, you'll get a transition between those. That's actually not that uncommon in wet environments, and in the tropics, not that uncommon. The large fluctuations depend on a number of factors. So if you've got a system that's got quite a large groundwater storage, you probably won't see much change. In other words, let's say it's a porous sands and gravels. The transmissivity of the gravels is so high and the porosity is so high that you tend to get not much change. It's pretty static. But if you have a relatively low permeability and just fractured, so let's say classic fractured rock, then you might see a significant change in groundwater level. And that's when you'll see those changes between the two types. The other indication I didn't say, of course, is that if you've got lots of green grass around, then you're probably in a wet environment. So the reason I put that in there is just to give you a feel for the different environments, which, as those of you who've been to East Africa know, is tremendous. It's one of the most diverse areas in terms of habitat and environment that I can think of, and so you can go a very short distance and be in completely different examples. In fact, most of the photos I took came from Ethiopia, all one country.
Okay. Thank you. Thanks.
I had a question.
Jonathan. Go ahead, Jonathan.
Hi, Malcolm. Thanks for the toolkit. I had a question about we recently had we recently sank 2 shallow bore wells in Kampala, about 35 meters deep, and we couldn't get a drilling rig anywhere near because it's such a built-up area. We couldn't get a drilling rig in, and so our colleague in Uganda, Philip, suggested why don't you use one of these mini piling rigs, which came on the back of a lorry and was lifted over using a HIAB into this compound, and we use that. Basically, it's the originally intended for drilling bored piles, and we use that to sink the casing 35 meters. Have you come across that sort of thing else being used before?
So it's not specifically a piling rig, but the old Pilcon tail on the back of a Land Rover rigs, which are percussion rigs, excuse me, are in very widespread use here in the south of England. And what they would do there is you ram your steel casing in, and then when you're ready to construct, you put your well casing in, put the gravel in, and then jack up the steel casing back out again, and there's your well. So that's the same method of percussion that you get with. I'm assuming it was it a percussion rig or a boring?
It seems to me it was rotary. It was drilling.
Oh, rotary. Okay.
And they were using there was an awful lot of water be used to flush.
Yes.
Oh, so.
Yeah. No, I hadn't come across that. I mean, reality is if you can put a hole in the ground, you can produce a well. It may not produce as good a well, but if your main purpose, if you're not trying, if your yield is that the capacity isn't important, that kind of solution is perfect.
I mean, it's just for a hand pump. So.
Yeah, there you go. So exactly that sounds to me like a really good way of getting around the problem. That 100% for your bush engineering.
Yeah, well, that was Philip Benderani's idea, so it worked. It worked fine. So.
Yes, yeah, it's great. Actually, if you have any background information, I'd be intrigued. So be good to catch up on that one.
Okay.
We've had a couple of, well, 3 questions. First of all is, can we have a PDF of the slides, which I think we can probably circulate to the CED list, if you're happy to do that, Malcolm.
Yes, I'm happy to do that. I was assuming that would be the case.
Yeah,
and
thank you.
It was written in such a way so that because nobody remembers an equation, so you'll need to have that to refer to.
Yeah. And Graham's asked the question, how do you determine if bore well contractors are credible? What things do you look for when choosing bore well contractors?
Yeah, so that'll come up in talk 3, because it's one of the biggest bugbears of drilling wells, is the fact that you're in the hands of the driller. So it's a real challenge. So spending as much time as you can to go and visit them, understand their attitude to drilling wells, whether their attitude to detail, their attitude to giving you what you want will tell you an awful lot, and whether you're going to have a handful or whether you're going to have a smooth ride. And what the attitude of the driller makes a huge difference to how much angst is on the project. Yeah. So there isn't a hard and fast rule on that. Your contracting skills are just as important as your geology and hydrogeology skills in groundwater, and no different to any other part of engineering, but especially in boreholes, because you're totally in the hands of the contractor and they can pretty much do what they want once they arrive on site. And it's very difficult to argue, because they're going to be drilling a hole, whatever, and they're going to expect to be paid. So it's quite difficult to break that loop. And because contracts are not really widely used in East Africa, and you don't want to get a big price, you have to keep your contract to a minimum, which then means that there is a certain amount of trust and a handshake involved.
Thank you. There's a similar question, and from I don't know if you can see Gig Cox. I'll read it out. If you can see the chat. but I'll read it out. We've had surveys done with a percentage likelihood of water at 60 to 100 meters in Turkana Pokot, northwest Kenya. A Christian borehole chap, they must be good if they're Christians, from Nehemiah Construction Ministries has a rig close by, difficult road access, plenty of government or church boreholes in the region, cost about £7,500, money raised by a local church. Hope to have a CED engineer with us. Any warnings before drilling to maximize success? That's from Gid Cox.
Okay, so the probably the best indication of success is what people around you, the nearby boreholes, have achieved, and the depths at which they've been drilled to, and how much capacity they've had. In particular, when you do a survey to get information, you need to find, people always tell you about their successes. They very rarely tell you about their failures. So you have to be very careful to ask about failures. And this is true anywhere in the world, but especially in Africa, you need to ask the same question multiple times in different ways to see if there was any, just in case there's a communication issue, but also to make sure that that the anything that the person who's giving you information understands that something that didn't work is just as important to us as something that does work. In fact, more often it's more valuable than the information that does work. So the local survey is a really good way to sort that out, Gid. Short of looking at the solution, every site is unique, has its own unique features, so it's very difficult to give anything other than broad brush advice on that one. But given the location, I would say there's probably a fair amount of geological variation, but don't know that for certain. Making sure that you've done some desk study work in addition would help. So following through the ideas in the presentation.
Thank you.
Oh, sorry. Just one further thing on that. In terms of geophysics, if the plan is to put in a relatively deep well, it will be difficult to find a geophysical method that would be helpful, that would be low cost. So once you get into the zone of greater than 60 meters, geophysical solutions become expensive. So I don't think a geophysical solution would help you, Gid, very much. I'm assuming the target zone is below 60 meters based on the question. If that's not the case, then discount what I just said.
Thank you. I was quite interested with you saying it's a least risk solution. Well, when you think about the majority of the cost is the drilling, or it's certainly a very big element. It seems to be, the fact you might drill it and then find actually we didn't find water and we'll have to start again somewhere else. I think we've had experience with a project in Tanzania where that happened. We had to find a different location and drill deeper. Least risk solution. I guess that's just the nature of the beast.
It is, but equally, it's important to understand the information you're receiving. So, on the site that I showed you from Tanzania, which is close to Tanga, there is salt water at depth. Probably around about 50 meters, the salt water is present. And a drilling company carried out a geophysical study using an unrecognized Chinese instrument, which failed to pick up the fact the salt water was there, which is one of the easiest things to do. So the value of that was clearly not very valuable. And then drilled straight into the salt water and provided a saltwater well. So the solution, as you saw in some of those pictures, is dug wells, because they pick up the shallow water. But now there is a hole that's been punched through into the deeper aquifer, which may be an issue whenever that aquifer surcharges, which we don't know yet. So yes, long story short, doing the due diligence is really important, because that's what reduces your risk. And if you understand the information that's available, that will get you to the point where you'll avoid wrong steps. And because to be fair to the drillers, they were doing something that they probably had done 100 times and got fresh water. And this location is 20 kilometers or so inland from the sea. It's not a place you would expect to get salt water. But in certain environments, and in this particular case is one, if you carried out, as I did, a internet search, I discovered a paper which said the continental boundary fault was 1 kilometer to the west of the site, in other words, upstream. And that meant that there was a high risk of salt water in the location we were in. And so it proved. And the shallow system, shallow alluvium from the river alluvium system was the solution. And that's why dug wells are the right answer, but are actually more expensive than a borehole. So you wouldn't do that as your first choice. You would go for the borehole, which is what they did. So there's a complete logic basis to what was done, but the misstep was missing the fact that doing the depth study, and missing the fact that the geophysics was inappropriate, and they should have used a recognized method.
Yeah, thank you. We've had a question about linings, and I was thinking about running sand. We've got in our village, we tried to drill a borehole, and we ended up realizing that it needed to be lined rather too late.
Yes.
Is that for the next? Will you be talking about that in the next talk?
It won't be the next one. That'll be the borehole construction side of it.
Okay.
But again, with those kind of conditions, you have to chase casing before, and then pull out the casing after you've put your well in and your gravel. And that can, if at a village level, you can do that with jacks, as long as you've got a method that can chase casing. Excuse me.
Yeah.
So sometimes you have to drill at a larger diameter, put in the casing. If you're going to leave it in, you cement that in, and if you're going to leave it as temporary, you put in casing that's much the same size as the hole, and then drill on down to finish your borehole. Put in the well and the casing and screen of the final solution. Put in your gravel pack or formation stabilizer, and then retract the temporary casing and reuse it.
I suppose, what would the considerations be whether to line or not?
So loose and unconsolidated material is where you need the lining. So if you're in the soil layer, most of the time you need some form of lining. So if your soil layer in the saprolite goes all the way down to 20 or 30 meters, you're probably going to need to have lining. Except if it's running sands, that is. But if it's relatively firm soils, then the mud will cope with that very well, the drilling mud and drilling fluid. So you'll need to have a drilling mud that's appropriately conditioned and sufficiently viscous to make sure that the walls stay up. And instantly there's a whole topic on whether to use bentonite muds or whether to use biodegradable muds, which at our level probably don't matter, but at a municipal level they're very important.
Yeah. Thank you. I've got another question, but I just thought I'd keep it open to the floor.
Can I just jump in? It's Brian Darling. Hi there, Malcolm. Thanks for the talk.
Brian.
One of the things we've been sort of gradually picking up what the contents of the next two talks are, and that sounds very interesting as well. But I'm just wondering, have we sort of missed any subjects that you're going to cover? Things like the headworks of the well, and are you going to talk about pumps? Are you going to cover anything like storage and that kind of thing? What's just roughly your outlines for the next two talks?
So that's a really great question. So when it comes to pumps and the storage components and elements like that, because I've worked in multidisciplinary environment most of my working life, I typically handed that over to an engineer and said, "It's your problem now." I've done my job. There's a hole in the ground. go make it beautiful. So but yeah, so certainly the sanitation design and the borehole design will come up in the borehole design, the third topic. In terms of pumps and tanks, the information that I have is learnt by osmosis, and there are probably others who would talk on that and give better advice. But nonetheless, on the information on pumps is relatively straightforward, so I could certainly include that in there. And then the tank consideration is, from my point of view, is purely a water resources one. Is what's the capacity and how does it adequately provide sufficient storage to make the water supply resilient? And that's come up in our recent project where we decided to put in 2-day storage rather than 1-day storage, in order to cover the fact that we might get a power cut, and so that we could use mains power. And that way, if we had a power cut for a day, we'd still be able to have a supply. Obviously,
I just
yes.
on that, Brian. There's the talks, as we've said this at the start of this, are recorded, and they are all available on the YouTube channel. And we have had one on pumps. So if you go digging about in the YouTube channel, you will find one on pumps. And if there's stuff in there that, or there's stuff missing, or you would like more detail, then that would be helpful to know. But go and have a look at that.
Great. Okay, I'll take a look, because I hope it covers hand pumps as well as the actual electric pumps or other types of pumps.
Yeah, we have had quite a technical presentation on electrical pumps, but we've also had talks on hand pump type of.
Yeah. Okay. Thanks.
Any other questions? My question was about arsenic and iron, and whether there's any advice on those. I know arsenic's quite local in Asia, I think, in Bangladesh, countries like Bangladesh. But
Yes,
anything
correct.
about iron?
So arsenic, as you say, is primarily a local issue, and the fact that the local people weren't using groundwater in Bangladesh was a fair indication that there was an issue with water quality. And I won't say any more, just because it's there was a significant sum paid to the Bangladeshi government as a result of mistakes made by BGS. Or emissions would be more accurate way. They didn't take any water quality samples to establish there was an arsenic issue, and then that caused substantial issues. So that is a good one to bring in, though, Mike, and a good case study, because most if you're in most international environments, certainly in Africa, they won't require a very large water quality list to be analysed, but as an expert, you're essentially required to establish that the water quality is all of the water quality issues that there potentially are. And if there's any concerns, then you need to take a water sample and get it analysed, and that might not be feasible in country. So it might be necessary to do the basics in country and then bring a couple of litres back in the appropriate receptacles and have them analysed here in the UK. Which case you're looking at somewhere in the region of 250 to 500 pounds for a full screening sample. Now, some things can be avoided, so it's very unlikely that pesticides are used, so the pesticide suite can be left out. Similarly with herbicides, but you certainly would want to have fertilizers in that group, and then a full suite of chemical and biological. But the main issue comes in transporting this is you'll be asked questions: is it radioactive? And of course, if you don't know what the norm are, you can't honestly answer that question. And I've had this issue before now. So you just say it's a drinking water sample. it's intended for drinking water, and we just want to check it. Because the paper chase is such that we want to know what the answer is before you've had a chance to test it. That is a good aid memoir to say that whenever we're doing a water supply that we have responsibility for, then it is a good idea to get at least one water sample back to the UK for a screen to check that there aren't any other unknowns in that water supply that require a solution. With regarding to iron, in iron, it's nearly always all about oxidation state. So if you have well oxidized water, the iron will be in the iron 3 hydroxide condition, which is pretty much insoluble, and you won't have any iron staining to speak of. If you have reduced groundwater with reduced conditions, and you can easily measure this with an ORP meter, and if the ORP is negative, then you need to pay attention. Most of the time, you're wanting water which has a positive ORP in millivolts, but above 0, because that typically tells you that that there is some dissolved oxygen in the water, and therefore most of the chemistry issues are unlikely to occur. It's once you get into reducing conditions that you see the weird and wonderful appear, of which one of them is iron 2, and iron 2 is quite soluble. So when that comes into contact with air in your water supply, you get iron precipitation and causes all the staining problems. Most of the time, it's not a drinking water standard issue, but it is definitely a nuisance issue. And so you would then need to have it in a situation where you can oxidize it, bubble air through it, or leave it in a contact tank with air, and then filter it out. But hopefully, in most situations, you would hope to be in an environment where the reducing conditions aren't that low. And if the ORP is on the low side, then you should be asking questions about where's that groundwater coming from? Is it coming from depth? Are there other contaminant issues? And in that environment, I definitely want to have my screening sample.
Yeah. Thank you. I think we'll be coming to the end of the questions. We'll be able to let you rest shortly, Malcolm, but I don't want to miss out. Gid's asked another question. Is there any value in attempting to refurbish disused borehole sites, of which there are several we've identified, unfortunately without any history of why they're no longer used? And is there a way to use fiber optic cable to look down abandoned boreholes?
Yes, take the last one first. So yeah, absolutely. You could. There are downhole cameras that can be used to inspect wells. That's usually the best way of doing it. They're not always 100%, because sometimes the water is murky, especially if you have the iron issue that we just mentioned, and so you can't actually see very much. It just looks like looking through a pea soup's fog. They on the pricey side, you may not be able to find them in Kenya. I suspect you will. At least somewhere will have one though, because of the various different organisations that do geothermal and so on. They'll almost certainly have CCTVs for their wells. So yes, that's a very good solution if you can lay your hands on one and can get it to site cheaply to inspect the well. Depends on age primarily and the materials. If the well is more than we reckon about 50 years for a well-designed steel well in most environments. But if you're in an environment where there's a fair amount of fault movement, so rift margin or something like that, then it'll probably last a lot less than that, and it may well have a big kink in it, and the well will be damaged at some point at depth. Again, the CCTV camera will show you that, and it's a grand way to go and check it out. So that's if you can do that and you can find the solution to do that, that's a great way to go forward. So you can obviously buy these instruments, but I think they're in the sort of £20,000 range, but new. So finding beg, borrow, and steal is, well, probably not the steal, but certainly beg and borrow. It's probably the one you're in for that one.
Any other questions? Well, if I would say, as an auctioneer, I would say going, gone. Perhaps I should have said it a little bit slower, but thank you. I think we will conclude then. Just another huge thank you to Malcolm for such a lot of work. Very informative. We really appreciated everything that you shared with us, and we look forward to the next talks to come on the subject. Just also to say that this will be on CED's YouTube channel and available through the website in the near future. I won't make any promises, but probably tomorrow. And a reminder that our next talk will be on communications in the developing world, and that will be at 7 p.m. on Tuesday, 4th of March. I'm not sure who's going to be speaking at that one.
David Bookham.
David Bookham.
Yeah.
So that's brilliant. Thank you, David. We'll look forward to that. So thank you, everyone. I'm going to stop recording now.